there, Algebras, and welcome to our video on Chapter 13, Lesson 1 notes, all about arithmetic sequences. So this chapter 13, is going to uncover some patterns that we see in our sequencing when we're given an initial amount and then have some sort of pattern of change for the rest of our group of numbers that we're given. What we're going to discover is there's specific patterns that are arithmetic, there are specific patterns that are geometric, and there are specific patterns that are what's called recursive. And that's what we're going to work towards is recursive sequences. So we start with some pretty straightforward arithmetic sequences where, if you know, there is an ordered set of numbers where each successive term has something called a common difference. Every number in this sequence is called a term, and each one has its order. So in our case, the first term or the initial term is 4, then the second term is 12, then our third term is 20, our fourth term is 28. This ... here is indicating that whatever this pattern may be that has this common difference, it's continuing on into infinity. So we would call this an infinite sequence. It doesn't end. This pattern continues. We refer to all terms after these first initial 4 given to us as an nth term. So the nth means if I want to know the 10th term, then my n value would be 10, and that would give me the 10th term. So we'll start with, from here, finite and infinite. So finite sequences have a specific stop. This is a finite sequence. There is no ... There are 4 terms in the sequence. That's where it ends. However, this example has a ... This is an arithmetic sequence because if you look at the terms, there is a common difference. And that common difference is, well, how did we get from 2 to 5? We added 3. How did we get from 5 to 8? We added 3. How did we get from 8 to 11? We added 3. Our common difference is 3. So our D value or common difference is a positive 3. Is this sequence finite or infinite? If it has the ... this is an infinite sequence, and feel free to just circle. This sequence does not have an end. We would keep adding 3 and adding 3 and adding 3 and adding 3 into infinity to find more of the terms in this sequence. In the next example, 1 and 3 and 5 and 7. Well, to get from 1 to 3, we add 2. To get from 3 to 5, we add 2. To get from 5 to 7, we add 2. So our common difference is a positive 2. And the sequence is finite because there is no ... present. We are not continuing on to infinity with this pattern of adding 2. After 7, we're done. There are 4 terms in the sequence. That's it. So a little more info on the common difference. If we're adding to get from number to number, why am I calling this a common difference? Well, because technically when it comes to sequences, to figure out what the common difference is, you actually take the second term and subtract the first term from it. So when I was figuring out how I got here, I was actually doing it backwards. I'm supposed to go 3 minus 1 is 2. And then I do this with the third term and second term. So 5 minus 3 is 2. So far, I'm getting a common difference. So then last one, 4 minus 5, so the fourth term minus the third term, gives me 2. That's where I'm figuring my common difference. So it's called a common difference because I'm taking one of my terms and subtracting the previous term. And if I do that enough times, I should have the same answer every time I'm doing that subtraction. That same answer leads us to our common difference. So down here, we're asked to find the common difference of each sequence. So let me try this sequence and this sequence and see if you can try this sequence and see how we do. So we'll start here. Okay, let's do this correctly. 11 minus 3 is 8. Okay, let's hope we still get that. 19 minus 11 is 8. Okay, and 27 minus 19 is 8. What's my common difference? 8. By the way, finite or infinite? Infinite sequence because of the dot, dot, dot. So the reason I'd like to do this next one is because it gives us the sequence in decimals. When that's the case, when fractions and decimals enter into our purview, if the sequence is given in decimals, we want to continue kind of discussing the sequence in decimals. If the sequence is given to us in fractions, we want to continue discussing the sequence in fractions. So it honestly doesn't actually matter as long as we're talking about terminating or repeating decimals. However, it's just kind of etiquette with a sequence. If it wants to be in decimals, it represents as decimals. So here, again, decimals, 3 minus 1.5. So 3 minus 1.5 is 1.5. So hopefully that's my common difference, but let's keep going. 4.5 minus 3 is 1.5. I know it seems repetitive, but I still always check to make sure everything in the sequence is giving me this response. So 3 minus 4.5, or excuse me, 6 minus 4.5 is 1.5 again. So my common difference here, 1.5. My dot, dot, dot is indicating an infinite sequence. I'm going to pause for a moment for you to try the third one. Okay, welcome back. And hopefully you can see how I figured out my common difference here. So take the previous term take the second term, subtract the first term, take the third term, subtract the second term, take the fourth term, subtract the third term, and every single time I got -6. So there's my common difference. So you'll notice that if your sequence is increasing in value, that your common difference is positive. And if your sequence is decreasing in value, your common difference is negative. Okay. So next up, we are going to kind of continue doing this and fill in some subsequent terms as we go. So let's try this again, right? Find the next 3 terms. Let's find the common difference, and then let's do some fill in. So here, okay, let's do 21 minus 48. 21 minus 48. Okay, -27. -6 minus 21. -27. -33 minus 6. Oh, excuse me, minus -6 is, -27. So there's my common difference. It is an infinite sequence. And I know that because I've got this dot, dot, dot here. Now let's keep going. So let's take and find the next terms in the sequence. So -33 plus -27. That's what my common difference is. Oh, I'm getting -60. -60 plus -27. I'm getting -87. -87 plus -27. -114. There you are. Now notice that B is representing in fraction form. Let's see if you can answer these things using fractions as you go. And remember, you can figure it in decimals, but let's do the sequence the favor of representing it in fraction form. So give that a try. We'll pause that again for you to give that a try. So sequences are great because you're representing in a pattern, right? So what I recognized when I'm looking at this is I said, oh, okay, so my whole number is staying the same twice in a row, but look at my fraction. My numerator in my fraction, 1/4, then 3/4, right? So I look backwards. Oh, it was 3/4 up to 1/4. Well, wait a minute. That's adding 2/4 or 1/2 each time. So 2 more fourths, 2 more fourths, 2 more fourths, 2 more fourths. I still represent in a reduced form 1/2. and it is finite because there are no ... dots. So one of the big differences between the types of sequences is how they present if you were to graph the pattern on a coordinate plane. Now, of course, we'll typically be looking in the first quadrant and the fourth quadrant when it comes to this, because we'll typically be looking at, well, we'll only be looking at positive nth terms, because you won't have a negative number of things in your sequence. So you can only have starting at 1, then 2, then 3, then 4. And if this represents your x value in graph form, then you can only be positive. So you'd only be quadrant 1 or 4. Your answer to that, what is the value of the nth term, that will represent with us as our y coordinate as we graph. So that's why I say that particular, the value of the nth term, that might be a negative number itself, but you can't have a negative number of terms. So we're only going to be in quadrant 1 or maybe 4 at best. All we really need to see is a pattern, though, of our distinct points. So what we're going to do is we're going to start with 1, the first term in our sequence, which is 0, and we're going to graph that first as a coordinate. Then we look at the second term in our sequence, which happens to be 2. So 2, 2. The third term in our sequence happens to be 4, 3, 4. And the fourth term in our sequence happens to be 6. So 4 all the way up to 6. Now, there are not any terms in between these 4 terms. So we have discussed prior to this that this would be a discrete graph because we will not be connecting these points. There are no terms in between to connect these dots together. All right. But if I could connect these dots together, what is the function that would form? That's a linear. That's a line. So what kind of function is it? Arithmetic sequences present themselves as linear functions because of that common difference. That common difference is always the same. It's always a number being added to the previous term, added or subtracted from the previous term, which means it's equivalent to having a constant rate of change, having a slope. Well, it also turns out there's a specific formula that we can use to figure out the nth term as long as we have our initial value, our common difference, and which term we want, what the term number is we want. And that specific formula is right down here at the bottom of our paper. So representing this pattern in our arithmetic sequence goes as follows. A to the subscript n, so that's the nth term that we're finding, is A, the initial value, plus D times n minus 1. And the reason for that is this is your first value, right? Your A is your initial value, or your y-intercept, as some of us call that, right? Your D ends up being your slope. We only apply that to all the numbers after the initial value. So that's the reason we do this subtraction right here. So what does A stand for? Again, the initial value. What does D stand for? The common difference, which is what specifically makes this arithmetic as a sequence. Excuse me. What does N stand for? The term number desired. This is the term number we want. So if we want the 9th term, N would be 9. If we want the 68th term, N would be 68. All right, so let's apply this. What I'll do is I'll take and I'll rewrite this formula on the next page because it really isn't written on this page. So right up here at the very top, let's start by doing that. A to the subscript n equals A plus D times n minus 1. Okay. Now let me use that in the first example to find the sixth term. You use that in the second example to find the second term. Here we go. So, okay, 86, 77, 68, 59, dot, dot, dot. So we are continuing on to infinity, infinite sequence. Let's figure out what that common difference is. So there we go. Oops. So 77 minus 86 is -9. Okay. 68 minus 77 is -9 again. Let's hope that continues. 59 minus 68 is -9. So our common difference is -9. What was our initial value in our sequence? That was this 86 right here. And we want to use our formula to find the sixth term. So the sixth just gave us our n equals 6. So now let's plug in. So a to the subscript 6 is equal to, our a value is 86, plus our d value is -9, times, in parentheses, 6 minus 1. And we can plug that right into our graphing calculator. So 86 plus -9 times 6 minus 1. So I recognize that a lot of this arithmetic is stuff that we could probably do in our heads, but we do also have this graphing calculator to double check ourselves. So I highly encourage you to make sure that you're correct with your answer by plugging in here. So we get that our sixth term in the sequence is 41. Now, let's be realistic about this. I had my first 4 terms. If I just kept subtracting 9, I'd get here, right? So 59 minus 9 is 50. 50 minus 9 is 41, our sixth term. So just a little proof that this formula is working for us. So why don't I pause here? You try number 2, and let's see how we do using that formula on our own. And we're back. Did you get the ninth term to be 20? Here's our plugins, our initial value, -36. You can see where I found 7 to be my common difference, and you can see where I was asked for the ninth term in the sequence. So 9 minus 1 is 8, 8 times 7, 56, plus -36 gives me +20, or just plug right into that graphing calculator. So please make sure you write out the formula so that you can make sure you're plugging into the formula correctly. Go back and check out those vocab words. Make sure you're comfortable with those, what the A is, what the D is, and what the N is, so that we know what we're finding as we go. We will actually be using most of those letters again as we look at the next type of sequence, geometric sequences, in the next video. All right. Get started on that homework. Let me know if you have any questions. Good luck, algebras. I'll see you soon. Bye.